Trieste. And she studied sample of AGN in high resolution and in local AGN, and her supervisor was Fabrizio Fiore and Chiaro Ferrudi, and she is continuing his research with her PhD student, PhD course, and today he is going to present part of his study.
Thank you. So the main topic of my presentation is the AGN feedback and the interstellar medium properties. Sorry.
Did you share on the Zoom link the presentation? No.
No.
Sorry.
Which Zoom link?
Okay. Wait. I will send you the link.
Through email. There is, okay.
Can you send me your email?
I can write you.
Yes.
MA Junk Design
Okay. Sorry, but we were full taken with the problem.
Okay. Did you receive my email? No. Però connesso, mi sono arrivate delle email. No. Eccola. Ho messo solo. Ok. Perfetto, adesso fai lo sharing sullo schermo, se no da non vedo niente, ecco. Ok, non faccio
Perfetto,
fai lo sharing, perfetto, semplicemente. Ok. Problem, presentazione, perfetto. Ok. Sì, vabbè, perché qua sto a fare, fai more, leva questo coso. Hide. Ok. Sorry. Okay, today I will present you my work about the AGN feedback and interstellar medium properties in the nearby universe. To start, this is a brief outline of what I will show you today. I will start with an introduction about the AGN feeding and feedback. Then I will show my results, and then I will go through our conclusions. First of all, AGN feeding and feedback is a key ingredient to shape galaxy formation and evolution. There are very strong evidence of links between the supermassive black hole mass, so on subparsec scales, and the property of the ROST, so on kiloparsec scales, such as the relation between the supermassive black hole mass and the velocity dispersion of the bulge that are reported here. So we have the feeding process, so the star formation process in which the gas is converted into stars, and then the AGN phase, the phase in which the supermassive black hole shine at a luminosity that is proportional toward the mass accretion rate. And then we have the feedback. We have the injection of energy and momentum into the interstellar medium. In this case, winds, shocks, or jets driven both by AGNs and supernovae can impact into the interstellar medium, removing or eating up the gas. In this context, we have these radio jets or AGN-driven winds that can drive outflows in the different phases of the gas, from the neutral atomic to the ionized molecular gas phase. And the gas, therefore, the gas of the gas is impacting their feedback. We have two main modes of feedback. The kinetic mode that is observed in the brighter cluster galaxies, in which these strong radio jets impact into the intercluster medium and drive cavities. In this case, these jets can keep halo hot, preventing further accretion in the star formation process. In this case, this type of feedback is observed in objects with lower end duration and in radio load objects. But what I want to focus on is the radiative mode feedback. So when the AGNs drive these outflows that detected in the different phase of the gas. In this case, the impact of the AGN is still not very well understood, but there are very lot observation of these AGN-driven winds. Here report is Zanchettin in the nearby universe, and Zanchettin and the very strong outflows in Mrk509 and NGC2992. The winds can impact differently into the interstellar medium. There are the outflows can be energy momentum driven, depending on if the energy is conserved or not. And these different impact of the outflows into the interstellar medium shape differently the relation between the supermassive black hole and the velocity dispersion of the gas of the host. Here reported an example, and this is a plot for Vittoria 2017, when the blue lines represent the relation from energy-driven outflows. So what we want to understand is if these AGN-driven winds can impact on the host galaxy star formation process. So we have to take into account different ingredients: the time scales of gas conversion into stars, the fraction of gas converted into stars and accreted onto the supermassive black hole, and the spatial scale affected by the AGN activity. How can we answer this question? We can study how the properties of the host is locally modified. So we can study how with high resolution data individual galaxies. Or we can study global effects. So how the scaling relation and integrated properties are different in AGN sample and normal star forming galaxies at different redshift. Here I show you some results from literature. On the left, there is the result. This is the gas fraction, so the ratio between the molecular gas mass and the star mass as a function of the stellar mass. And in red, local Seyferts galaxies, and the other normal star-forming galaxies. And as you can see, in this case, the gas fraction is higher at here is higher at lower stellar masses. Instead, on the right, you can see the gas fraction always as a function of the stellar mass. In a sample, the stars represent a sample of 8 quasars from Biscetti et al. 2021. And as you can see, the gas fraction in this case is lower at higher masses. And they point out that this could be due to the black hole feedback effect that decrease the gas fraction in the host. But my work is mainly focused in a sample of local nearby object, the IBISCO sample drawn from the integral AGN catalog, in order to be unbiased against the nuclear obscuration. And here I show you the same results from the IBISCO sample, and also in this case the gas fraction is below the relation from star-forming galaxies at higher stellar masses. And this could be due to the fact to the AGN outflows that inject energy and entropy, affecting the gas cycle in the host. And what we can study also is the Schmidt-Kinetic relation. Of course, the main ingredients in this case are the molecular gas mass and the star formation rate. This is on the left is the relation from that data 2010, and inside here are the black points are from Casasola et al. 2015, and here this is what I found from NGC2992, that is part from the IBISCO sample. And what we understand if these are relation differences in the Smith-Kinetic relation, especially resolved in AGNs and in normal star-forming galaxies. This is something we are doing for the whole IBISCO sample. And this is this is some maps from the IBISCO sample. This is something still ongoing. Here I show you instead some results from a work in individual galaxies. This is the Mrk509, a local type 1.5 Seifert. These galaxies show different outflows in different gas phases. An ionized outflows detected through O3 emission, ultra-fast outflows in the nuclear region, and ionized wind in absorption in the UV. And moreover, there are also it also been claimed that it is in an ongoing minor merger with gas-rich dwarf galaxies due to the presence of this tail and this jet that you can see here. We have studied the molecular gas in this object with ALMA CO221 data at 270 parsec resolution. What we have found is that the CO is mainly reserved in a molecular disk, coincident with the starburst ring detected in the optical images, and with a molecular gas fraction that is consistent with normal star-forming galaxies. And so this molecular disk with ongoing star formation and the starburst ring, the minor merger, are in agreement with the scenario in which the gas destabilization is due by the mergers feeding both the AGN and the star formation process. We model the kinematics of the gas using 3D Barolo by Vittoria and Fraternali, and we found that the kinematics is consistent with an inclined disk plus an inner warped disk. But what we found is that we found also kinematical perturbation that here are labeled as A and B. And we identified this perturbation as molecular winds with velocity between 200 and 250 kilometers per second. What we found is that region A overlaps with the ionized winds at a similar velocity with respect to the ionized wind. Therefore, probably we are seeing a cooling sequence of an AGN-driven wind that is consistent with momentum conserving and energetic or rotation pressure of dust. Instead, the other kinematical perturbation is coincident with the starburst ring, and also its energetics is compatible with supernova-driven winds. For what concerns this stability, we also derive the TUMR gas parameter in order to understand if the disk is stable against gas fragmentation. What we have found is that the disk is stable both at nucleus and in the outflow region. Instead, it is marginally stable at the starburst ring. Therefore, at the location of the winds, the star formation is suppressed. Okay, and then I will show you another sample of the individual object, the local Seyferts NGC2992. In this case, we analyze 3 different data sets, radio data from VLA, and ALMA data that are tracing the continuum and the CO221 emission, and the MUSE data tracing the optical counterpart. And this is a cartoon, probably is not very well seen. You can see the VLA emission, the CO disk traced by ALMA, and the O3 emission from MUSE. For what concerns the continuum, we found that the radio data show a H-shaped structure of about 1 kiloparsec. Plus these two regions that overlaps the dust disk traced by the ALMA continuum emission, they're reporting out that this emission is due to the star formation process. And then for what concerns the disk, we found that both MUSE and ALMA data are able to trace a multiphase disk with the same inclination and similar rotational velocity. But for what concerns MUSE, we found a higher velocity dispersion in the ionized gas with respect to the cold molecular gas. But with ALMA, we were able also to distinguish an inner circumnuclear ring that you can see from this PV diagram that is taken along the major axis of the disk of the rotation. For what concerns the ionized gas, we computed also this is something very technical, so I will keep it but it is very important to derive correctly the ionized gas mass, because the main uncertainties in the ionized gas mass is the electron density. Okay, so the molecular outflow, we found evidence of perturbation to the disk-like kinematics in two regions for what concerns the molecular gas, in edge 1 and edge 2. Unluckily, in edge 2, the kinematics is very complicated because the NGC2992 is part of a system, and in here there is a tail that is connecting NGC2992 to its companion NGC2993. But we found also clumps of molecular gas outside the disk that we identified as outflows. For what concerns the ionized outflows, this is we use the O3 emission lines to trace the ionized gas kinematics. In this case, we found evidence of outflows both in these two big cones and also in the nuclear region. This is the spectrum. As you can see, there is a very broad wing that is tracing the gas outflowing at the nucleus where no molecular outflows detected. In this object, it is very interesting. We found also from literature the extended X-ray emission that, as you can see, probably is not very well because the contours are very light, are superimposed in the region with the radio. So probably the shock width is eating the gas on a scale of 700 kiloparsec. This gas emits X-ray forming this hot bubble, because this is not a jet, these are bubble. The ionized wind entertain the molecular gas from disk and lift it's up. Okay, to put all these things in a more wide context, what we found is that both in Markarian 509 and in NGC2992, the molecular outflow rate is below the correlation found by Vittoria et al. 2017 for a sample of AGNs. Probably because this sample is biased towards positive detection, and this highlights the importance of a study outflows in unbiased AGN samples. And this is an agreement also of what found by Ferruglio et al. 2020 in ESO 428. Okay, this is our, we'll skip it. Probably this is our evidence of outflows also at a higher redshift and a very high redshift. This is some very new results from Bischetti et al. 2022, studying very nuclear outflows in ionized gas at redshift V6, where probably we are seeing the moment in which the black hole is accreting much more with respect to its galaxy host. And this, what is also important to put these outflows in a wider context, so to study outflows, but also its galaxy host, understand how these outflows impact on their host. And this is an example at higher redshift. All of them are maps obtained with ALMA with very high resolution data. And this is something, show you some preliminary results from the recent months. What we are studying also is the nuclear region with AGNs. As you probably know, AGNs are distinguished in type 2 and type 1 objects depending on their spectra if the nuclear region is obscure or not. And so we have type 2 that are obscure, in which we cannot see the broad line region, instead type 1 in which we can see the broad line region. But what it has been found by Manizzi et al. 2020 is that there are some exceptions to these schemes. There are absorbed type 1 objects and unabsorbed type 2 objects. A lot of them are characterized are change in look object in X-ray and intermediate type, so type 1.8, 1.9. And they suggest that in this case, we are seeing the torus based on the absorption not to the torus, but to the gas on galactic scales. To understand that this is something that is plausible, we want to study correlation between the molecular to the gas column density derived by the molecular gas and the one derived through X absorption, through X-ray band. These are some results from Garcia Burillo et al. 2021, and from a subsample of 14 galaxies from the Gato sample. They claim a positive correlation. I don't know if it is true, honestly. And we try to do more or less the same using also data from the IBISCO sample. And what we found is that in ESO 428, there is a claim that the molecular gas is contributing to the X-ray obscuration. What we want to do is to understand if there is a positive correlation, and if this correlation depends on the type of the AGN. In fact, we have submitted a proposal to NOEMA with also Angela and Manuela Molina. And then I will conclude my presentation with this result about the velocity dispersion in the star-forming galaxies and in the AGN. These are results from Hubler et al. 2019. This is the velocity dispersion of the ionized gas as a function of the redshift. As you can see, the ionized gas seems to increase its turbulence with increasing redshift. From a low redshift, we have a velocity dispersion of about 30 km per second. Instead of a higher redshift, we have a velocity dispersion of about 50 km per second. What we want to do is to study the velocity dispersion in AGN host. So this is how we can do it. Of course, we need high resolution map. Why resolution? Because we need a resolution unless the mismirroring in the central region of the galaxy play a dominant role. This is some example of velocity dispersion map, both at redshift 0, at redshift 4.6, and at redshift 6. So with this high resolution data, this is for the ionized gas. First of all, this is we were able to derive the velocity dispersion in NGC2992 and ESO 428. In this here, this is the velocity dispersion around the nuclei and in the disk. This is for the redshift 6 quasar J2310. And what we found is that in this case, the velocity dispersion is above the relation found from Hubler et al. 2019. But of course, a statistical sample is needed, and also data with high both spatial and spectral resolution is needed, because you have to take into account that ALMA have very high spectral resolution, instead the MUSE have a very lower spectral resolution comparing with ALMA. For what concerns the molecular gas, what we found is that here these are our results have a lower redshift, and then for other, these are individual objects, of course at a higher redshift. But as you can see in this object, the velocity dispersion is above the radiation found by Hubler et al. And we are studying the velocity dispersion in the IBISCO sample in order to increase our statistics and understand if at low redshift there is an increase of the velocity dispersion. Okay, and then these are very more recent results from Ritz et al. 2021. In this case, they point out that the high resolution T+ data of the 10 dusty star forming galaxies are redshift 4 that are here. These are dusty star forming galaxies are below the correlation found by Hubler et al. Because from Hubler et al. The correlation is studied up to redshift 3 and then it is extrapolated. But the point, they claim that the point is that you need very high resolution data to be able to derive the real velocity dispersion, unless your velocity dispersion is increased artificially by the beam smearing effect. For what concerns our high redshift data, we found that both TO and T+ emission in the high redshift quasar J2310 indicated that the velocity dispersion is still increased in this high redshift quasar. These are our outside points, but of course it is a single object also because there are very few objects in the ALMA archive with such high resolution. And so this is my conclusion. What we have found is that the molecular outflow rate in the local Seyferts galaxies is below the best fit correlation found for molecular winds in AGN by Fiore et al. 2017. This highlights really the importance to study these properties in unbiased AGN samples. We have very strong evidence of multi-phase disk and outflows across the cosmic time, both at low and high redshift. We seem to have found, but we have to study better this, a positive correlation between nuclear galaxy scale obscuration in type 2 misclassified AGN, but this is also only a claim. You have to go deeply on this topic. And then we have also an indication that the gas turbulence is enhanced in AGN hosts with respect to star-forming galaxies. This could be due to an effect of the AGN-driven winds on their galaxy host. And that's all, and thank you for the attention.
Questions?
Great, thank you. Vittoria. Can you go back regarding the last point, the previous slide? Okay, you basically propose that the higher turbulence may be related to AGN feedback and winds. So all your data points, the blue ones,
okay,
are those showing strong winds or not?
Yeah, this is okay. This a low redshift. This is a NGC2992, Mrk509 and NGC2992. Yeah, at higher redshift there is a
high data point.
Exactly.
And also the other two.
Exactly. The point is that they are individual objects. That's of course the point. But the point is that the problem is that the beam smearing. So you need the high resolution data, and Francesca highlighted very well that the point is that you have to ask ALMA a lot of hours to get this high resolution data on individual objects. So
my point is that if you trust these values of sigma,
okay,
the interpretation that is the higher turbulence may be due to AGN feedback may be the case, especially for the three cases at high redshift, where indeed we see basically mostly the strongest molecular outflows.
That's true. That's true. The point is that you can do the same discussion as the one I'm doing at low redshift, that you need the unbiased sample of AGN to do something like that. The point is that a low redshift, it's quite easy because you are in the nearby universe. You don't have to ask for a lot of hours to ALMA. You can study. Of course, if you have a low luminous object, a higher redshift, you have to ask probably an amount of, and to justify for such a high resolution observation.
We had this discussion with the Nobel Prize.
Okay.
More questions?
How do you say it?
It's not.
Perhaps?
Yeah, I'm not at all working on question on mainly how you estimate the molecular gas.
Oh, okay.
So
Yes,
what sort of
sure.
alpha COs do you use?
Okay. Okay. Of course, you detect the CO emission. In this case, we use the CO221 emission. Of course, you have to go to CO10 emission, then to convert the luminosity to the molecular mass. Of course, you have to use a conversion factor that strongly depends on the metallicity. For this low redshift object, it is we have estimated for every single object the conversion factor.
You have the metallicity.
Yeah, exactly. So for the viscous sample, you have a strong uncertainties when you do it for the gas in the outflows. But because in that case, you don't have the same conversion factor. So in this case, there are strong uncertainties. As you can see, I show like the range for the mass in the outflows, because you can have a optically thick or optically thin gas. In this case, also the conversion factor changes. Of course, if you go to IRESH, the uncertainties increase a lot. But for what concern the gas in the disk, we have the metallicity. So for what concern that, less uncertain. Okay.
More questions?
Thank you. Can you go back a couple of slides?
What?
A couple of slides.
Here? No. Here.
No,
Okay.
no. I don't know.
Okay.
No, this one. Yes.
This one?
Yes.
Okay.
So I don't know what's the spatial scale probed by IBISCO.
In this case, the ALMA data have a resolution in between 100 and 200 parsec.
Okay. Instead of the Gatos one is much higher resolution.
Exactly. But
So-
this is something we are trying to.
Okay, but I was wondering, you said earlier that the Schmidt-Koenig relation breaks down below 100 parsec. I was wondering, have you tested these against the different spatial scales?
This is something we want to do because these are different data, of course, as you point out, because here the resolution is much more
That's
higher.
my concern.
Probably it is due to circumnuclear rings, stuff like that. Instead of 100 parsec scales, we are. We are trying to understand. This is something ongoing, and we are exploiting ALMA archive, and for a lot. These are also IBISCO, and these are very well-known objects. So some of them are have a different data set with different resolution. And what we were talking also about with Angela is that this correlation could be also depend on the Seyferts type. So we should understand what we want to study, because probably if you put all the things together, you find like a scattering. Because here I don't see a positive correlation, honestly.
No, but this is a very high spatial.
Yeah.
So, some of those galaxies are around 20, 50 parsecs.
Yeah, I know. It's like
And
one
this relation
order
could
of
be
magnitude
very-
difference.
So for example, they find that the nuclear region, the ISM in the nuclear region is slightly affected by the AGN, but out to 200 parsec, they don't find any correlation.
Yeah.
Many other studies at lower resolution, they find a huge impact over even 1 kiloparsec.
Yeah, because with ALMA, if you have such high resolution, you are also filtering out all the emission of higher spatial scale, so you are losing something. Of course, if you have a lower spatial resolution, you are smoothing, but you are not filtering out. So this is a point to take into account, of course.
Thank you.
Okay, one last question from Viviana, remotely.
Oops. Yes, thanks. Hi, Maria Vittoria, piacere. I have a question about the Koenig-Smith law relation plot. where you compare two galaxies of your sample with my sample published
Now
into.
only one object, two regions, one object.
Ah, okay, two region, okay.
Yeah,
Two
yeah.
central region, right?
Yes. And these are these two regions.
Okay, okay. And you derived H2 mass from CO120 line, right?
Yeah, exactly.
Okay, by using the conversion factor from the Milky Way.
No, as I told before, we have the metallicity, so we have derived the conversion factor by using the metallicity of this object. It's
Okay.
Milky Way-like, but it's not one of the Milky Way. For the IBISCO, we have a conversion factor for every object. So
Okay, and for my sample, you plot 6 stars.
yeah.
Okay, but my sample consists of four galaxies.
But different
regions.
regions, because
No.
here two
Different lines, not regions, because we sample the same nuclear regions, but okay. I will read the paper, so thank you.
Okay. Yeah, but this is something we are doing.
Okay. Since we are late, let's thank again Maria Vittoria.